Imagine a calm, darkened room. On one wall, there is a screen waiting in silence. On the other side, there is a soft beam of light, steady like a breath. Between them sits a simple plate with two thin openings. Two small doors, side by side, cut like eyelashes into a smooth surface. We let the light pass through these slits, and then we walk around to the screen to see what happens. We expect to see two bright bands, two neat lines of light, as if the being were two pencils drawing with certainty. But what appears instead is a series of delicate stripes. Bright, dark, fading slowly outward, like ripples on a quiet lake after a pebble drops. This pattern is called interference, and it is the signature of waves. It is what water does. It is what sound does. It is what you'd expect from something that spreads, overlaps, and adds to itself. And this is the first whisper. Light, which for centuries is argued to be made of tiny particles shooting in straight lines, now paints the wall with the fingerprint of a wave. A pattern of presence and absence, of bright interference and dark cancellation, as if the light is talking to itself, as if it passes through both slits and meets its own possibilities on the other side. Now we change the experiment. We make the beam so gentle that only the faintest trickle of light gets through. We allow just one photon at a time, like single snowflakes falling into a quiet winter night. One after another, over and over, each tiny packet strikes the screen. You might think the picture would become just two clusters where each particle lands. But when we collect enough of these solitary arrivals, the stripes slowly reappear. The interference pattern grows like a photograph in a darkroom. Each single photon behaves as if it took all possible paths, then interfered with itself, as if it was a wave of possibilities that later became a single event. That is the second whisper, and it is louder. It tells us that the world at small scales does not behave like the world we grew up in. Things can be both spread out and local, both wave-like and particle-like, not because we are confused, but because reality itself is layered with possibility. When we look closely, the quiet hum of existence becomes a dance of chances. We might ask gently, what if we try to watch which slit the photon goes through? It feels natural to check. We could place a tiny detector at one of the slits, a little observer, a careful eye to see the path. But something delicate happens. When we measure which path the photon takes, the interference pattern fades away. The stripes soften, then vanish, replaced by two simple clusters, as if the photon made a choice. Our act of knowing changes the picture that the world paints. This is the heart of the double-slit experiment. It is not just a clever trick with light and openings. It is a window into the deep workings of nature, where the act of asking a question changes the answer, where possibility flows like a river and then hardens into a single stone when we touch it. You do not have to hurry here. Take a slow breath. Let your curiosity move at the pace of a tide. The double-slit experiment has been repeated with light, with electrons, with atoms, even with large molecules made of many atoms holding hands. In every case, if you do not ask which path the particle took, it behaves like a wave and creates interference. If you ask which path it took, the pattern of waves collapses into something else, something more familiar. The world seems to care about what can be known. How did we arrive at such a gentle paradox? How did a pair of thin openings invite us to rethink reality? The story begins before quantum physics had a name, in an era when light was already a mystery, and people were just starting to discover that nature often hides her rules in simple experiments. It begins with a scientist who projected ripples onto a wall and saw with his own eyes that light can behave like water. But the deeper story, the one that changed everything, only revealed itself when we learned to count one particle at a time. For now, imagine you are standing beside that screen, watching the delicate bands grow, bright and dark, presence and absence. You raise your hand to the slits, wondering what would happen if you tried to peek. And you feel the quiet magnet of curiosity asking the simplest, oldest question there is. What is this world made of, really? The answer, as it turns out, will ask something of you in return. It will ask for patience, for a soft attention, for a willingness to hold both pictures in your mind at once. Wave and particle, path and no path. A thing that is spread out like a fog, and then a moment that is specific, like a drop of rain on your skin. We are about to walk through those two thin openings into a history of ideas. We will meet the people who drew lines on paper and then found those lines in the sky. We will watch as the calm face of classical science ripples into something stranger and more beautiful than anyone expected. Take your time. On the other side of these slits, the world is the same as it was, but our way of seeing it will be new. In the early days of science, light was a traveler whose nature kept changing depending on who was telling the story. Isaac Newton, with his sharp intuition, imagined light as a hail of tiny corpuscles, little particles that bounced and refracted much like small stones on a pond. Christian Huygens, a contemporary with a different temperament, pictured light as a wave that spreads through a medium, the way ripples move through water after a pebble lands. For a long time, these visions coexisted like two languages describing the same countryside, each useful, each incomplete. What turned the tide was a demonstration so simple, so visual, that it quieted many arguments at once. In 1801, Thomas Young, a gentle, curious polymath who studied languages and optics and even deciphered ancient scripts, arranged a beam of sunlight to pass through two narrow slits and cast a pattern on a screen. He saw the neat bands of interference, not two bright spots. The sight was not so different from the ripples you can make in a shallow pan of water with two fingers tracing side by side. Where crests met crests, the water rose higher. Where a crest met a trough, they canceled. Light was doing this too. It was interfering with itself. Young's result threaded itself into the fabric of science. Slowly, carefully, other experiments supported the wave view. Augustin Jean Fresnel built a theory of diffraction and interference that matched what people saw in laboratories. A pool of mathematics began to grow around the idea that light could be curled and bent like a fluid of pure brightness. The two-slit pattern moved from being a curious picture into a quiet proof. Decades later, the work of James Clerk Maxwell gave that proof a deeper voice. He wrote down equations that connected electricity and magnetism. Within those equations, something elegant appeared. A self-sustaining wave that needs no medium. A wave of electric and magnetic fields dancing around each other at right angles, moving through empty space. Maxwell calculated the speed of this wave. It matched the measured speed of light. Light, he realized, is an electromagnetic wave. The universe did not need a hidden substance for waves to ride on. Empty space itself could support this rhythm. With Maxwell, the wave story of light became rich and precise. Experiments measuring reflection, refraction, polarization, and diffraction all lined up like notes in a harmony. The classical world, as we often call it now, felt stable. Objects had positions and velocities. Waves had wavelengths and frequencies. If you knew the initial conditions, you could predict the outcomes. When young students learned about Young's double slits, they learned it as one of many illustrations that light is a wave. Yet small tremors were beginning. Black body radiation did not follow the rules expected of waves. The ultraviolet catastrophe, a poetic name for an impossible prediction, told us that something in our assumptions was missing. Max Planck introduced the idea that energy came in discrete packets, quanta, to fix the numbers. He thought it was a trick to get the right answer. It was more than that. Then Albert Einstein, thinking about the photoelectric effect, proposed that light itself comes in packets, photons. When light hits certain metals, electrons are ejected, but the energy of those electrons depends on the frequency of the light, not its intensity. A brighter light at the wrong color does not help. Only light of a high enough frequency can liberate an electron, and when it does, the energy it gives has a specific, discrete character. This observation is particle-like. It is not the way gentle waves would give up energy. It is the way a rain of pebbles would. Photons are not little billiard balls, but they carry energy in steps. A puzzle formed. Light interferes like a wave. Light exchanges energy like a particle. Which is it? The double-slit experiment sat quietly in the background, a picture on a wall that refused to be painted over. Many scientists thought that one of the pictures must be incomplete, or that the particle idea was just a workaround. A sigh, a shrug, until something better came along. The surprise came when we turned the question around. If light, long considered a wave, behaves in some ways like a particle, what about matter? Could particles sometimes behave like waves? Louis de Broglie, a thoughtful prince with the heart of a physicist, proposed that every particle has a wavelength. Not metaphorically, but literally. A moving electron, a moving neutron, even a moving molecule has a wave character. The wavelength depends on momentum. Large objects have wavelengths too, but tiny ones. So small that the wave nature of everyday things is buried in its own silence. Once you hear this, the double-slit experiment becomes a soft invitation. If electrons have wavelengths, we should be able to see them interfere. We should be able to send them through two slits and watch as they paint the same stripes that light does. And if we dim the electron source, if we let them pass one by one, we should see a pattern build up, arrival by arrival, as if each electron traveled the many possible paths and then made a single dot. This was not a metaphor to those who tried it. It became a plan. Clinton Davison and Lester Germer, working with nickel crystals, saw diffraction of electrons in 1927. An electron beam reflected off a crystal showed peaks and valleys of intensity that matched the predictions of wave interference. Around the same time, George Paget Thomson, the son of J. Thomson, who discovered the electron, observed electron diffraction passing through thin metal foils. The electron had become both the most delicate of particles and the quietest of waves. If you sit with that gently, you can feel the ground shift. The double slit is no longer just about light. It is about matter. It is about anything that can move. The world, at its root, does not choose between waves and particles. It wears both, and which outfit we see depends on the questions we ask and the devices we place in the path. Walk back into the calm room. The slits are still there. The screen is still waiting. But now imagine changing the source. Photons, electrons, neutrons, even complex molecules, like buckyballs made of 60 carbon atoms joined into a hollow sphere. Experiments have sent these larger systems through grating-like slits and watched interference patterns grow. The wave nature of matter extends farther than intuition would like, right up until interaction with the environments smudges it away. The boundary is not sharp. It is a gradient of fragility. We are approaching the point where language starts to split. We need new words, or we need to let old words stretch. Soon we will talk about wave functions, probabilities, and what it means to measure. But try not to tense up. Let the ideas flow around you. They are trying to tell you that the world is richer than a single picture. The double slit is a lens through which we can see the seams of reality, where what can happen interferes with what else can happen. And what we choose to know decides what pattern is allowed to appear. In the next step of this story, a new rule enters, one that does not scold, but it does insist. It says that the universe offers us a spread of possibilities, and that the square of a wave tells us the chance of each. The rule did not come with a comforting picture at first. It came with a promise that matched the experiments. We will hear that rule, and we will watch it play on the canvas of the double slit like moonlight on a gentle tide. Close your eyes for a moment and listen. Imagine the soft ticking of a detector. One click, then silence. Then another click. Each event is discrete, a point on a screen, a moment in time. And yet, from these points there rises a pattern that speaks of a wave. How? The answer, fragile and powerful, lives in the way science learned to think about possibility. Erwin Schrödinger, inspired by de Broglie, wrote an equation for waves of matter. It looks like a cousin of the equations for vibrating strings and surface ripples, but it describes a wave function, not a physical wave in water or air. The wave function, often called psi, spreads across space. It evolves smoothly. It interferes. But what it represents is not a density of stuff. It is a density of chance. Max Born brought that insight into focus. He proposed that the square of the wave function's magnitude is the probability of finding a particle at a particular place. Not a hidden ignorance, not a shrug. A fundamental feature. With Born's view, the double-slit experiment finds a new voice. The wave function travels through both slits. The two branches of possibility overlap, creating an interference pattern of higher and lower probability. Where the wave function peaks align, the chance of detection is higher. Where a peak meets a trough, the chance is nearly zero. Each individual detection on the screen is a single punctuation mark. Taken together, they reveal the grammar of the wave function. The pattern is not a ghost. It is the portrait of possibility. Werner Heisenberg framed another key part. The uncertainty principle is not a curse on measurement, but a rule about the world. Position and momentum cannot both be precise at the same time. The more tightly you try to squeeze one, the more the other spreads. The double slit is a living picture of this. To create interference, the paths through both slits must remain indistinguishable in principle. To obtain which path the particle took, you must interact with it in a way that correlates its passage with a record, which is another way to say you inject information and momentum blur. The result is that the paths become distinguishable and the interference fades. Niels Bohr called this complementarity. Nature presents different aspects depending on the arrangement of the experiment. Particle-like or wave-like are not two separate beings, but two faces of the same coin, revealed by the questions we ask. To try to force both faces to show at once is to misunderstand the coin. A double slit tells us this gently. Do not try to hold the ripples and the stones at the same time. They are the same water, but different experiences. Richard Feynman, with his chalkboard and quiet humor, told his students that the double-slit experiment contains the only mystery of quantum mechanics. He did not mean the only problem to solve. He meant that all the strangeness is present right there. If you can accept what happens at the slits, you will find the rest is an unfolding of the same logic. He showed another way to think about it. In his path integral approach, a particle takes all possible paths between 2 points, each path contributing a little complex number, a tiny arrow. Add all those arrows, and you get an amplitude. Square its length, and you get a probability. The double slit is a play of arrows. Paths through one slit and the other, and many zigzags. If the two slits are open, paths through both contribute and interfere. If we close one slit, we remove a family of paths. The pattern changes. If we place a detector that can reveal the path, we entangle the particle with the apparatus. The phases of the arrows no longer add in the same way. Interference vanishes. That word, entangle, is patient but deep. It means that systems can become linked in such a way that you cannot describe one without the other. Measurement is not a passive glance. It is an interaction, a weaving. In the double slit, a which-way detector, even a very gentle one, leaves a trace. That trace is information, not necessarily knowledge in a human head, but a correlation in the physical world. And the mere possibility of that information, in principle, is enough to change the pattern. This is one of the most subtle lessons. You do not need to read the data to change the outcome. You only need to make the data possible. Scully and Joule's quantum eraser experiments made this soft and startling idea vivid. They built setups where path information could be marked and later erased. If the which path information remains available, interference disappears. If, by some careful trick, the information is made fundamentally unknowable again, interference can be recovered in a special, sorted set of data. John Wheeler took the thought further with delayed choice experiments. He showed that whether you look for wave-like or particle-like behavior can be decided after the particle has passed the slits, even after it has been detected, depending on how you select and analyze the data. The lesson is not that we change the past. It is that the experiment's full context determines the correlations we see, and quantum correlations do not care about our classical intuitions for sequence. As techniques improved, scientists slowed the world down to almost a stop, observing single photons, single electrons, single atoms tracing their own lonely bright spots on a screen. They watched the interference pattern grow one event at a time. Each arrival felt like a decision, yet the collective picture was a poem written by a wave function. The beauty of these images is practical. They are not artistic renderings. They are records of the raw conversation between possibility and outcome. Neutron interferometry added a flavor of Earth and gravity. By splitting and recombining neutron paths, researchers showed that these neutral particles, drifting through crystals, accumulate phases in response to potentials and rotations. Matter waves are sensitive to the world's quiet curves. Later, with cold atoms, people built Mach-Sender interferometers that measured tiny forces with exquisite precision. The double slit lives in all of these devices. Two paths or many, made to meet again, and an interference pattern that encodes what happened along the way. Even molecules, complex and warm, can be coaxed into behaving like waves if they are isolated enough from their environment. Interference has been observed with molecules composed of hundreds of atoms. The patterns are delicate, easily disrupted by heat or stray collisions with air. That fragility is a hint of something we will touch soon, something called decoherence, which helps explain why our everyday world does not shimmer with giant interference patterns. But before that, stand again in the imaginary quiet room. Listen to the hush. Imagine a particle that is not a pebble, but a probability cloud, drifting through both slits. Imagine a detector that softly registers a choice. Imagine how a change in what can be known quiets the ripples. The double slit changed physics, not only by surprising people, but by teaching us how to ask questions without pressing too hard. It told us that nature is not a stubborn puzzle to be forced open. It is more like a lake at dawn. If you thrash the water, the image of the sky breaks. If you are still, the reflection returns, and the world above and below the surface become one for a moment. In the next breath of this story, we will look at how the lake stays still or becomes disturbed. We will talk about decoherence, which explains how the world's many interactions blur phase information. We will see why cats in boxes are metaphors, and why computers that compute with superpositions are possible, at least in principle. We will look for the line between the quantum hush and the classical chorus, and find, not a line, but a gradient of noise. If the double slit is a poem about possibility, decoherence is the weather report. It tells us when and how the poem can be read. It is a process, not a person. When a quantum system interacts with its environment, even lightly, information about its phases leaks into the world around it. Think of a violin string vibrating in a quiet room. You can hear the pure note. Now place the violin in a busy cafe. The sound is still there, but the noise mixes with it, and soon the clarity blurs. In quantum terms, the phase relationships that give rise to interference are like the tuning of a chorus. Decoherence is the way the chorus loses its perfect alignment when too many voices sing without listening. In the double slit, decoherence arrives when scattered photons, air molecules, or nearby fields carry away which path information. Not necessarily the full story, but enough to make the paths distinguishable in principle. Once the environment has recorded a trace, the interference pattern fades, even if no one ever reads the record. The universe itself has observed in a gentle, unsupervised way. This explains why we do not see people walking through doors and interfering with themselves, or planets choosing all possible orbits at once. Large objects are in constant, intimate contact with their surroundings. Their wave functions are entangled with everything, so quickly that any delicate phase pattern dissolves before it can spread. Decoherence does not solve every philosophical question about measurement, but it does give a practical answer to why the world appears classical at our scale. It tells us how superpositions become mixtures, and why, when we look, we find definite outcomes rather than delicate fringes. It connects the mathematics of entanglement to the texture of daily life. It also helps design experiments. To see interference with large molecules, researchers must cool them, shield them, and let them fly through vacuum, so that the environment cannot steal the phases. The success of such experiments is not just a stunt. It is a proof that the quantum rules do not stop at the border of atoms. They persist, conditionally, as far as we can protect them. This realization has consequences that are not quiet at all, even if we embrace them softly. The same interference that draws stripes on a screen can be used to enhance, suppress, and guide probabilities in devices. Quantum computing is, at heart, a choreography of interference. A quantum bit or qubit can be in a superposition of states. With a series of gates, which are controlled interactions, we can make the amplitudes associated with correct answers add, and those associated with wrong answers cancel. It is as if we built tiny double-slit stages in a high-dimensional space, arranging the paths so that only the desired pattern survives. The math is demanding. The picture is poetic. We are not using magic. We are using the same rule that makes bands of light and shadow. We are choosing which questions to ask so that the answers interfere in our favor. Interference is not only for computation. It is a tool for measurement. Gravitational wave detectors like LEGO are colossal interferometers. They send laser light along arms, bounce it between mirrors, and recombine it. A passing gravitational wave stretches one arm and squeezes the other by a whisper of a distance, less than 1,000th of the width of a proton. The interference pattern shifts. A fringe moves. The instrument listens to cosmic events by watching the quiet dance of light. This is the double-slit spirit, scaled up and tuned to the deep bass of the universe. In medicine, interference patterns in MRI and advanced imaging help us see inside without cutting. In materials science, electron interference underlies electron microscopy, letting us view atoms arranged in lattice. In everyday life, semiconductors and lasers, children of quantum understanding, power the devices that carry our voices and thoughts. When you tap a screen, you are living with the descendants of those two thin slits. Let us return to the gentle heart of the puzzle. Why does which path information erase interference? An analogy can help. Imagine two musicians playing the same melody in separate rooms. If the rooms are connected and the doors are open, the sounds meet in a hallway. If the musicians are exactly in tune, the notes rise and fall together, and a beautiful pattern emerges in the hallway. Now place a small recorder in one of the rooms that captures a faint trace of the melody. Even if no one plays it back, the presence of the recorder changes how the musician in that room listens and adapts. A tiny, unavoidable shift enters. The phase relationship between the two players becomes fuzzy. The hallway pattern blurs. In quantum terms, the system and the recorder are entangled. The phases that used to be relative to each other are now also relative to the recorder. When we ignore the recorder and look only at the hallway, the interference washes out. The quantum eraser invites a reversal. If we can, by design, ensure that the recorder's trace is erased or made indistinguishable, we can restore the pattern. Experiments have shown this with photons entangled in pairs. By choosing how to measure one, we can sort the data from the other into subsets that reveal or do not reveal interference. This does not send information faster than light. It does not change the past. It shows that the pattern is not a property of the particle alone, but of the whole experimental arrangement and the knowledge embedded within it. Where does this leave our intuition? The double slit does not ask us to abandon it. It asks us to soften it, to accept that particles are not little marbles, and waves are not ghostly fluids, but that the world has a structure where the basic object is neither thing nor ripple, but a wave of possibility that becomes an event when it interacts. That becoming is often called collapse, but collapse is not a physical shove. It is a word for the update of our description when a particular outcome occurs, usually through entanglement with a vast environment. Different interpretations of quantum mechanics tell different stories about what this update means. Many worlds suggest that the wave function never collapses. It branches. Each possibility continues in a different, non-communicating branch of reality. Bohmian mechanics proposes that particles always have definite positions, guided by a quantum potential that carries wave information. Objective collapse theories say that superpositions break spontaneously when they become large enough, adding a faint new rule to nature. Cubism and related views place the emphasis on the personal nature of probability. These are quiet philosophies, cautious around claims that cannot be tested. In the lab, the equations work the same. The double slit remains as it is. Stripes when you do not ask. Spots when you do. If you rest inside this, you may feel a calm familiarity rather than a shock. The world you know is still here. Your hand still has a shape. Your breath still moves in and out. The double slit does not make the floor vanish. It adds a layer. It tells you that behind the solid, there is a soft field of potential. That behind the everyday, there is a shimmering map of what could be. It gives the cosmos a deeper kindness. The universe is not brittle. It is supple. In this softness lies a humble lesson. Our questions matter. They are part of the weave. The experiments we design, the choices we make about what to measure and when to look, do not merely reveal nature. They participate in it. This is not license to wish outcomes into being. It is an invitation to treat reality as a conversation, not a monologue. And that conversation can be as practical as a chip etched with nanometer precision, or as philosophical as a late-night thought about why a single photon paints a picture of a wave. We stand near the end of our walk, but not at an edge. The double slit opens into a field of ideas. One more step, and we can ask what this means for us, not as a technique, as a way of seeing. What does it change in the way you place your feet on the ground, or the way you look at the stars? What does it whisper about choice, chance, and the beauty of being a small, curious mind in a vast, quiet universe? Let the room grow quiet again. Picture the slits, the screen, the soft beam. The experiment is almost impossibly simple. A light source, a barrier with two openings, a place where the results collect. When we look at the pattern after a long while, we see something both clear and mysterious. The world holds shapes of possibility that only show themselves when we do not press too hard. It also holds the warmth of single events, each dot a little heartbeat of actuality. The double slit does not ask us to choose between awe and understanding. It offers both, slowly, like tea poured into a thin cup. How did this experiment change physics? It did more than correct a formula or measure a constant. It changed the questions. It took the idea that reality is made of little objects moving along little paths and softened it into a larger picture, where paths are stories we tell only after the fact, and what truly evolves is a wave of chance. It told us that the act of making distinctions carves the world into the pieces we then see. It taught us that knowledge is not separate from the physical, that information has weight, not in grams, but in influence. It birthed the science of the possible, where the brightness on the screen is a probability before it is an event. Spin forward through the years. With the double slit as a guide, physics built a framework where atoms are clouds of probability, where electrons around a nucleus are not little planets, but standing waves. Chemistry, the shapes of molecules, the colors of minerals, the efficiency of photosynthesis, the glow of LEDs, the transparency of glass, the sharpness of a laser beam, all rest on quantum rules that the two slits made visible. The world of the very small became not just imaginable, but describable, predictable, and in many cases controllable. A phone in your hand, a GPS signal from satellites, a medical scan that sees what your eyes cannot. All of these are quiet echoes of that pattern of light and dark. The experiment also changed how we talk about truth. Classical physics gave us a clean confidence. If we know everything now, we can know everything later. Quantum physics replaces that with a compassionate humility. The wave function gives a complete description of what can be known, and at the moment of interaction, a single outcome is realized. The humility is not a defeat. It is a promise that curiosity remains relevant, that there will always be a pattern to discover, always a way to improve the clarity of our questions. On another level, the double slit offers a personal metaphor that many find soothing. Your life is a spread of possibilities. Plans, hopes, fears. Most of them will not happen. Some will. The pattern that emerges is shaped by the questions you ask, the attention you place, the interactions you allow. When you look back, it can seem as if a single path was inevitable. But just as interference patterns are built from many potential paths meeting, your way forward is often better served by keeping more than one path open for a while. By allowing yourself to be wave-like when the world is wide, and particle-like when it is time to commit. This is not airy self-help. It is a way of moving through the world with gentleness. The double slit suggests that clarity comes from context. The context you set for yourself matters. Choose environments that protect your delicate phases when you need to dream. Choose interactions that collapse your hopes into action when you need to build. There is a time to let probabilities sing and a time to listen for a single click. The experiment also carries a whisper about connection. Entanglement says that parts of the world are not always separable, that the phrase, "this thing alone," can be misleading. In a time when many of us feel isolated, it is comforting to know that the deepest level of description insists on relationships. A photon is not only itself. It is itself and the slit and the screen and the field around it. You are not only you. You are you and your history, and your surroundings, and the people who stand with you. Identity is a pattern within a greater pattern. In physics, this is not poetry. It is prediction. In life, it can be a soft hand on the shoulder. As we end, let your thoughts drift for a moment to the night sky. The starlight you see has traveled for years, sometimes for centuries, sometimes for longer than we can say without whispering. That light has threaded its way through dust and field, and at last it meets your eye. Inside your eye, on a tiny patch of living tissue, a photon of old light gives up its energy to a molecule, and a signal begins that your brain will recognize as a star. Without knowing it, you have just hosted a small, personal photoelectric effect. You have converted wave-like possibility into a definite event. You have collapsed a tiny piece of the universe into your own experience. The double slit is there too, in the way that light would have interfered with itself if the conditions were right, in the way your eye is an environment that ends the wave's journey. Perhaps that is the deepest gift of this experiment. It asks us to participate with care, to set conditions that allow beauty to appear, to remove, when possible, the busy noise that erases delicate patterns, to meet the world with questions that do not bully, but invite. Science at its best is exactly this. Not a battle against darkness, but a tending of the light, the way a gardener tends a quiet path at dusk. The two slits are simple. The room is simple. The screen is simple. The consequences are vast. Physics changed because nature showed us clearly and gently that what is real is richer than what is obvious. That the smallest things carry the largest lessons. That possibility is not vagueness, but structure. That a pattern of light and shadow can teach us how to listen. Thank you for walking through this with me, slowly, with patience and wonder. If you would like to wander through more calm stories of science, you are welcome to stay close and subscribe. We will keep the pace gentle, the curiosity warm, and the night sky within reach.